Let's move on to the model managing. Up to now, we have presented various experimental model authoring methods for tires, suspension, bush, and body with test data-driven MBSE technologies such as in-situ TPA, VPT, FBS decoupling, experimental model, and SEMM. As I said, these test models are authored compatible with simulation models. However, we need to unify the unit system, point naming, and analysis condition to couple them. After converting them to a standard format, the models are ready to be coupled in a network database with global access. The next step is to make max use of these models for virtual vehicle development. At first, we make a virtual vehicle using component-based TPA or virtual prototype assembly. Then we evaluate the target and perform detailed analysis such as transfer path analysis and model sensitivity analysis. Finally, we can listen to the road noise results for subjective evaluation as we did with an actual vehicle. To realize the virtual development environment at our worksite, we integrated MBSE toolchain, simulation, and test side. Regarding test side, we have been taking advantage of commercial software and our own software developed for local site use with the intimate cooperation of SimCenter Engineering and Seoul National University for several years. Let's move on to the verification of what I have explained up to now. To clearly show how credible our model-based approach is, we compared the result from conventional vehicle-based measurement with new experimental model-based estimations step by step. At first, we compared the interface force from tire to suspension in 5 directions as follows. We found similar force profile between two approaches, which verified the credibility of experimental blocked force and transfer function model of our tire system. Next, we compared the target road noise measurement from the various estimations, such as classical TPA with vehicle-based measurement and component-based TPA with 2 models, and virtual prototype assembly with more than 4 models. It was found that among vehicle and model approaches, they showed similar road noise profiles, which verified the credibility of suspension, bush and body model, and overall model coupling process. Finally, we compared the transfer path contribution map across 20 paths and found very similar results between vehicle and model approaches. After a strict verification, I can now say that our structure's model-based virtual development approach can provide an environment where we can do almost everything that can be done with an actual vehicle, so-called equivalent virtual vehicle model.
After strict verifications, we have made max use of experimental system models for road noise development for modular architecture in HMG. At first, as our test model was originally designed to be compatible with the simulation model, the test model has been co-used with the simulation into a hybrid virtual vehicle model. Second, the system test model could have been used as a system-level correlation tool more efficiently than conventional vehicle-level correlation. Finally, we adopted blocked force to better understand the tire's behavior and share clear component targets with our suppliers early in the development phase.
Let's move on to our last topic, oralization, which means replaying and listening to road noise assembled with load and transfunction models before a physical prototype was even built. By coupling models, we can perform objective evaluations such as pass or fail compared to the target. However, until now, not enough subjective evaluations was done, which has been done with actual vehicles. So, we built the traditional top-down vehicle oralization model with various contributors such as powertrain, tire, and wind. Also, we replaced road noise contribution with hybrid model combinations. This enabled the developers to listen to road noise from model changes at their discretion, which was impossible with the conventional system. To simulate various driving conditions, we made a database cube to retrieve a proper model depending on the driver's input. In the beginning, we have been developing a desktop simulator in cooperation with SimCenter Engineering, in which the designers can listen to road noise resulting from model changes, such as tire, bush, and body, on various driving conditions such as road type and speed. As a further step, a dedicated virtual evaluation platform will be implemented using the driver's input device, vehicle performance models, and visual aid in HMG.
Now, let me conclude this presentation briefly. Digital Engineering Center has been developing test data-driven MBSE technology consisting of model authoring for securing representative, compatible, and credible models, and model managing for presenting objective and subjective evaluation platform to developers. These research activities have been reinforcing model-based virtual development in HMG.
For a future plan, we made a technical roadmap. There are remarkable two tracks. At first, we will develop test data-driven MBSE technology to expand MVH coverage. Then we will complete the virtual development platform with an objective and subjective evaluation function. That's all I have to say today. Thank you for your attention.